Today, we're diving into something that sounds like a total contradiction: the hidden dangers of machines that are working perfectly. It's a problem that's completely changing how we think about safety. So think about this for a second. You have a self-driving car. No broken parts, zero software bugs, not a single glitch. Everything is running exactly the way the engineers designed it to. And yet, it still causes a crash. This isn't just some brain teaser. It's the single biggest challenge that autonomous vehicle safety is facing right now. To really get our heads around this, we have to kind of throw out our old ideas about what makes a car safe. We're about to explore a completely new kind of danger. Okay, so here's the core idea. There's a new safety standard called SOTIF, and it starts with this wild assumption: a system can be unsafe even when nothing is wrong with it. The focus completely shifts from, fixing failures to managing the built-in limits of the technology itself. This is a huge shift in thinking, really. For decades, what we're calling old safety was all about preventing stuff from breaking. A bad motor, a faulty chip, that was the enemy. But new safety, or SOTIF, is way trickier. It asks, what happens when all the parts are working perfectly, but the way they work creates a hazard? A sensor might be doing its job perfectly, but it still gets confused by the world. And that right there is the new frontier. All right, let's make this feel a little less abstract. We're going to break down a real-world example to see exactly how a perfectly fine system can cause a really dangerous situation. We're going to use a classic example: phantom braking. I'm sure you've heard of this. It's when a car, out of the blue, just slams on the brakes. There's nothing in front of it, no danger, just a sudden, heart-stopping halt. It's a textbook SOTIF problem. So to figure this out, engineers have this two-step process that's all about separating the what from the why. Step one is about identifying the hazard, which is just a fancy way of asking, what did the car do wrong? Easy, it braked for no reason. Step two digs into the system itself to ask, why did it do that? It's a really critical difference. First, you identify the dangerous action, then you go find the root cause. So here's how the investigation plays out. Step one, we've got the hazardous event. The car slams on the brakes. That's our what. Step two, they find the why. It's something they call a functional insufficiency. Then, step three, they nail down the root cause. The car's 2D radar can't tell how high things are, so it sees an overhead highway sign and thinks it's a car. And finally, step four, they find the trigger. This only happens on one specific curve where that metal sign reflects the radar signal just right. See? Nothing's broken. The radar is just doing its job, but it has limits. So, the engineers understand the problem perfectly now, but this is where they face a really tough choice. I mean, how do you fix a problem that isn't technically a broken part? They've basically got two main paths they can go down. Strategy A is, the head-on approach. Just make the technology better, make it smarter so it can overcome its own limitations. Strategy B is more like a strategic retreat. If you can't solve the hard problem, you make the problem simpler by just avoiding the situations where it happens. So if they go with strategy A, they could do a hardware upgrade, swap out that 2D radar for a fancy and way more expensive 4D radar that can sense height. Or they could beef up the software, maybe use the camera to double-check what the radar is seeing. Another way is to just train the AI with thousands and thousands of pictures of highway signs until it learns, okay, ignore those. But, all of these can cost a lot of money and take a ton of time. Now, let's look at strategy B. Let's say you're testing a car's LiDAR sensor in the fog. The data comes back and it's crystal clear. In light fog, zero chance of a collision. Awesome. But as soon as that fog gets thicker, the risk just goes through the roof. The tech has a very clear, very measurable limit. So instead of trying to invent a sensor that can see through pea soup fog, which might be impossible, the engineers make a smart, data-driven call. They restrict the car's operational design domain, or ODD. That's basically the rulebook for where and when the car is allowed to operate. In this case, they program it to shut off if the visibility drops below 45 meters. They didn't fix the sensor, they just smartly avoided the problem. And this brings us to what is, without a doubt, the hardest part of an engineer's job. I mean, it's one thing to fix a known issue like phantom braking, but what about all the dangers you haven't even thought of yet? In the SOTIF world, you can sort of map everything into 4 boxes. You've got things you know are safe, you have things you know are unsafe, like our phantom braking example, but the real enemy, the thing that keeps engineers awake at night, is that unknown unsafe quadrant. These are the bizarre 1 in a million scenarios that nobody would ever think to test for. So, the entire goal of this whole SOTIF validation process is to be a hunter. It's about systematically shrinking that scary, unknown, unsafe territory. You have to actively search for these hidden dangers, drag them out into the light, and turn them into known unsafe problems. Because once a problem is known, you can fix it. But how in the world do you find something when you don't even know what you're looking for? Well, you basically use an AI to attack your own system. Engineers run these massive simulations where an algorithm's only goal is to try and make the car crash. It starts with a near miss, and then it intelligently starts twisting the dials, making the road a little slicker, the other car a little faster. It evolves the scenario over and over again until, bam, it finds a hidden weakness. It's like a guided missile for finding breaking points. But here's the thing, even with millions of miles of simulation, you can't possibly predict everything. The real world is just infinitely weird. And that's why the safety work doesn't just stop when the car leaves the factory. In this world of SOTIF, launch day isn't the finish line. Nope, it's the starting gun for the biggest testing program you can imagine. Every single car on the road becomes a data-gathering sensor, helping make the entire fleet safer. And the key technology that makes this all possible is called shadow mode. It's basically a silent version of the self-driving software that's running in the background while a person is driving. It sees everything the car sees, it makes decisions about what it would have done, but, and this is the important part, it never actually touches the controls. This creates this incredible continuous feedback loop. So let's say the AI in shadow mode was about to change lanes, but the human driver suddenly jerked the wheel back. The system flags that disagreement and sends a little data packet to the engineers. They look at it and discover, whoa, the AI totally missed that motorcycle splitting lanes. That's a brand new unknown unsafe scenario found in the wild. So they develop a fix, they test it, and then they push it out to every single car through a software update. The entire fleet just got smarter overnight. And that really gets to the core philosophy here. Safety isn't some checkbox you tick off. It's not a test you pass once and then you're done. It's a living, breathing process, a constant cycle of discovery, fixing things, and adapting to the real world. Which, of course, leaves us with one last huge question to chew on. As these systems get smarter and can drive in more and more complex situations, will we ever actually stop finding new unknowns? Or does every single step forward just open up a whole new universe of risks we haven't even imagined yet?